Okay. Hello, everyone. I'm pleased to meet the audience and I didn't expect that much crowd. So I will start from a short historical introduction, how all that happened and from what I started. It will be about procedural creatures and Voronoi fractals, the mostly procedural things. In the beginning, I tried to invent algorithms that are actually generating animals. Animals are from multicellular animals made from cells. I did have a vision to make a intro that is showing the procedural creatures, and it was shown at Assembly 2005. Maybe someone seen it already. It is 64K, all done by myself, including music, which some people didn't like. It's a procedural tree over here. Actually, it's a simple recursive tree. I will show later how it's done. This is Voronoi Fractal. It rocks and the creature that is animating. The creature is also creature is also made from recursive rules. It has many self-similarities, like in fractals. I will stop the intro soon because how much people didn't see this actually. Okay, so maybe I will show a bit more. Yeah, so the caves, there are some underwater caves I made also from cells. Everything is from cells because I have basically obsession with cells and Voronoi, and also what you can do with cells. You can do a lot with cells, and this is just a short introduction. There will be some fun. This is also from rule-based model. Okay, I will break this, nothing interesting later. There's some fancy... It is a DNA or something. Yeah, that should be all. Okay. So, what is fractal? Fractal is something that I will not give you a definition because mathematicians might be sad about it, and I will just say that I'm calling a fractal something that is iterative, made by an iterative process. Basically, you know, or you all know probably L systems for trees or Tomkh fractal, the Snowflake Fractal, for example. I did what I'm trying to do is to give ability to make easy fractals by visual tools, very easy to use. For example, if you want to make a Tomkh snowflake, you just put few segments. This is not me generating this sound. And just set the segments that one segment will be substituted with another segment. This is simply done, but I'm all creating it in real time, and you get a Tomkh snowflake. You can move it, and you can do many advanced, more snowflakes that are made from simple substitution rules. This is all edited in this visual tool. You don't have anything to program, to code. This is the basic idea to give the possibility to explore fractals by being an artist. There are also some quad-based, and let's add more iterations. Where's the plus? Oh. The problem is it's a keyboard. Oh. there's a recursive rule for making hands, and the same rule for let's say legs. It's just substituting one segment with a group of another segment and transforming whole group into this segment. Maybe I will just show one more thing. There is a tree. I fixed it yesterday. Oh, this is not right tree. Okay. So we can also control not only the iterative rules, but we can visually control when to substitute. You see this is those. Oops. Never mind. Those segments are all based on iterative recursion and derivated from the base model, and I can control when to substitute or not in higher levels of iteration. I can substitute this with here or this here, and it will all be propagated into the same segments in other iterations. It's really helpful to visually edit the iterative it's not fractal actually, it's like recursive tree. So the main task is to do it in 3D main problem. In 2D everything is more simple, and I will show you I did in 2D another approach. This is a creature, let's say, that is growing by subdividing from cells. When he eats something, something grows. He has more heads, and there's snake generalization. You know that snake just eats and his tail is growing, but this snake is eaten. It has loose a head. And is getting slower because the physics is the head is pushing everything up. How it's done? It's done in simple 2D editor. For creatures represented just as a spheres, the connections are automatically added to it. I have firing rules. AAA, it's a firing rules for the circular system segment. CCC is for tail. Another tail. If I press A, I will get more circular system. If I press C, I fire tail. I fire another tail. I can fire a head. Let's say circular system, head. It has another circular system, another head. Yes, and this is I can control what rules of subdividing I'm firing with simple visual tool. Okay, now I will show the same, but for you can. I also did the same for visual tool for just explicitly showing the subdivision of cells. You can do a cycle by this cell will turn into that kind of cells, this into that kind, and there's our connections. It's all visually edited, and you can make a procedural. Oops. It was wrong parameters. It's some, let's say, iterative subdividing each cell into two and generating some interesting shapes from it and with physics. It can also simulate some, let's say, organisms that replicates. It's very simple recursive. You can't do too much with it actually, because recursion is really limited to being very self-similar. If only parameterized recursion gives you a possibility to create really complex shapes. Okay, now there's the main. Oops. main part of my presentation. This is I did my own presentation system, and it's 3D, completely interactive. I don't know if anyone done it before. So this is title, and you get everything is done in 3D from cellular diagrams. Cellular diagrams is a generalization of Voronoi diagrams. The Voronoi is a special case of cellular diagram. In simple definition, a cellular diagram is just a set of non-overlapping convex cells. Those cells are actually inside there are like Voronoi diagrams, outside there are like spheres. Okay, now what is a Voronoi diagram? Voronoi diagram is a diagram that is defined that way. It's segments of Voronoi, the orange one, you can rotate of course, are where there's a very important thing of when you are defining such diagrams. You need to know what is a first closest distance, second closest distance, third closest distance to some set of points. You have at the input for the diagram you have a set of points, the black ones, and this is the input set of points. For every point of it's a projection of two-dimensional space. This is the two-dimensional space from different angles shown. This is just plane, and for every let's say point on the plane, you just calculate first and second closest. You don't have to calculate, but this is how I define the Voronoi diagram. Calculate first and second closest point, and if the distance to first and second closest point is the same, you draw a point here. So this is a line between, let's say, 2 points where the distance from to first and second is the same. So this is really not first and second. Maybe I should explain more the concept. For any point in the plane, you can sort the input points by the distance, right? You calculate the distance to every point and sort it by the distance. And that's where are in this sorted table first point, second point is the concept, first and second closest. Okay. The another diagram is spherical diagram. It matches the Voronoi by the segments, but has a circles around the diagram. It is also it can be made in different way. Normally, Voronoi there are many algorithms to calculate Voronoi diagrams. You don't have to check every point of plane, of course, and there are some iterative cell insertions, Delaunay triangulations, and computational geometry is the field that derived many interesting algorithms pretty fast. But this is a different thing, because you can calculate diagrams just between spheres that are intersecting. The diagram, maybe I will show. What I'm talking about. If I put a circle, another circle, the circles are intersecting in 2 points, right? This is obvious. And if I draw a segment between the 2 circles, I get the part of the diagram. If I add another circle, I also have the points that intersect. But if I join, clip those segments against these segments, I can generate the Voronoi diagram between those circles. And adding more circles just give me a diagram. It's all based on that intersection segments. And you can add, increase the radius of spheres and etc. and you get the diagram. Okay. Where was my presentation system is of course remembering the stage where we will have been. So the relation between that diagram and Voronoi diagram is actually, it's very similar. When we are changing radius of spheres, the cell for every sphere is getting is changing size relatively to another cells, and this is the same, exactly the same as power diagram. Maybe you know it from, it's very often in computational geometry you are dealing with power diagrams. It just those paraboloids are the visualization for the distance function, that is squared distance function, and where the paraboloids intersect, you just have a segment, as you can see. They intersect with Z buffer, and this is exactly matches the segments. Because of perspective, this is not that exactly matching here on the picture, but you should trust me, it matches. Yeah. So okay, so in 3D, you are starting with just spheres. A sphere is symbolizing a cell. I'm showing here the intersections of the spherical diagram, which is Voronoi, matches Voronoi. And that way I can edit the cellular geometry, and I can smooth it and get an interesting modeling technique. And you can simply do everything from just spheres, real time. This look very blobby because they are not really metaballs. This algorithm is working on spherical diagrams and relaxing the mesh after generating the independent cells. I can show you, maybe I will show you some simple, let's say it's a creature. We don't know if it's a creature, it's just a set of spheres for me. But the point is, this creature is actually made from cells. You can this part, and you can see the actual diagram between cells. Why I concentrated on making things from spheres, because spheres give you a chance to make generate actually geometry, not just edit like I do it here, but it's very easy. You don't have to care about connections between spheres. You just generate sets of spheres, random spheres maybe or something, and you get some shape from it. It could be done with metaballs, but I found that more funny to make from cells. It's also faster, and the metaballs are hard for making multi-resolutional modeling. You can, for example, here, let's say, add more detail to this fancy thing. And it has different resolution of blobs than dead blobs that are lower. If you show a mesh, this has higher resolution than this one. That gives you potential to add details at different scales. Now, that would be not that exciting if you don't have replicators. replicators are basically why I call it procedural. I show you the other ways in the two-dimensional examples of doing recursive systems. You can do the same here, but you have a group of spheres, let's say, and yes, and let's say we want to replicate a group. We just move it. And every change here is also changing in the replicated group. This is just like another instance. So if you move it here, rotate, and let's say remove this leg because it's not necessary anymore, and copy this leg here. And we get two legs, the same legs. But the trick is you can also mirror it symmetrically and rotate. So we have more natural legs which are symmetrically the same as legs. Our left leg is the same as right, but symmetrically mirrored. And what we can also do is do recursion. If we have a group of cells, we can replicate, but join it to the same group. Rotate, and see what happened. If you, the problem is, who knows how is page up in German? Here?
This one, yes.
Okay. So we can recursively add it legs. I will show some more advanced model that is reminding actually some kind of human shape. This is just made from few groups of spheres. This is all the definition of this model. And those are red spheres are replicators. Those are beginning of replicators. Let's say this is a hand, this is a finger. Yeah, this is a finger. You can have finger from any count of segments you want. This is not just a typical finger. It might be might be fancy finger, and now I have this fancy finger in hand. Of course, I can rotate everything real time. And I have, if I connect it to a hand, and now I have this all joined together. So this really really easy to control, and gives you some crazy possibilities. Okay. So what I also have here, Voronoi Cutters. You can, because this is made from cells, you can cut some part. How is home? Yeah. Ende? No. Post one. Okay. Yes, so I can remove some and see the. This is not a good model for this. I hope not to scare you because my woman is very scary. Are you ready? Okay, I warned you. It has cut off hand on purpose. You can show that. And let's say now we can cut off another hand. We don't have hands. It's all made from spheres. Mesh is really high quality. I think no T-joints or anything like that. And the base is from spheres. Quite ugly. Okay, this is some more. If you are doing some funny procedural creatures, you want to have many legs, many sticking out things like I don't know, some spikes, some who knows what else. So we can experiment and do something with 4 legs. Also rotate and everything is nicely replicated. I didn't use the feature I was showing in 2-dimensional case where I was showing the tree. In that tree I could not only replicate, but for example I will show a tree. Yeah, there is a tree. Let's go more into the recursion limitations. If you just do a simple recursion, you can only replicate the same shape recursively, and there's green spots are endings of recursions. And you don't, if advanced mode, you could actually connect another tree to the end of this every branch. This is what is not already implemented, but was implemented in 2-dimensional case. So I only have the same shapes replicating. If I would advance it, I will add it, for example, draw me a, let's say, human head on the top of the every branch. This could be possible, yeah, to do. Here you just have iterative tree. Yeah, this could be not blobby, but converted into cones. The skeleton is Voronoi diagram. Wait, something. Oh. That's the skeleton for the mesh generation algorithm, skinning. I showed it for 2-dimensional case. It's the slices between spheres, and I joined them using convex hull algorithm to make a mesh and then relax them, and it has a blobby property. Okay, that was the editor. I have also what you can do with cells, another part of this presentation, Voronoi Fractals. I had my own idea for a simple fractal that is infinity zoomable. It's just made from cells. You are starting from a set of random cells, tile them, and you get tiles of cells. You know, this all tiling. Oh, I forgot to show you that there is also tiling possibility, hidden possibility, because not yet. Yes, you can tile a shape in here too. That's possible. Actually, it would be funny to make a combination of tiling, recursion, and any other iterative schemes to make a real funny editor. Okay, so we can tile cells, and the idea to make a fractal is that those cells are now colored using random colors. as you can see. The idea is to color them from the resized tile. We are just dealing with tiles of cells and resizing it at every cell that is below. I should stop it. Every cell that is below the bigger cell is getting the same color. And the bigger cells are actually the same configuration of cells as smaller one, but are just bigger. It's the same tile. You can pre-calculate it, what cells numbers are changing colors from what bigger cells, and actually make a, I just have to find, it's very fast. And if you do it recursively, by enlarging the cells and copying colors, that cell will, in the middle, will be enlarged, and the colors will be copied to the smaller cells again and again. And you get fractal this way. I will show you how this fractal looks in, yes, this is the same fractal, but visualized two-dimensional, and you can, the cells are actually not visible because you see iterations up to 1 pixel, and it's infinitely zoomable. You can zoom everywhere you want, and you never lose the precision because there is no need for remember anything from the other. Actually, this fractal was on purpose made or on purpose looped in the scale, but it is possible to use 2 sets of cells and use randomly get colors from another set and mix them using some random seeds, and you have really long period of that fractal. You can have 4 gigabytes in 32 bits seed, and you will never see the you will never go into a loop in your life. Maybe no, I'm just exaggerated. Maybe with 64 bits seed, but the fractal is, as you can see, really very self-familiar. So there is no this is not maybe that exciting. Okay, the same fractal can be done, of course, in 3 dimensionals, and that was, but only 2 iterations. Not infinite. That was, cells are getting smaller and smaller and smaller, and up to 1 pixel size here. But if I don't do it and just do 2 iterations, I can have generate a landscape that is made from cells, but cells are actually visible. They are not 1 pixel size. I also did, but don't have screenshots with. It was not very. It doesn't look that nice because it's very high frequency noise. It's like a noise, but high frequency. And those are cells that I tiled. I can show. Yeah, this is a tile. This is a tile of 3D cellular tiles. It's very simple. Actually, it's not that simple to generate that kind of tiles because Voronoi is in general hard to code, and it might be nasty for detecting all the. It's computational geometry is always a problem to generate nice meshes, and without small epsilon staking and precision problems, you have all to deal with it. And if you replicate that tile, actually, that set of cells, and only pick some of these cells, you get that that kind of landscape, let's say. It's more like cave. We are going to the end of this presentation. I will just show you the what I did. This 10 minutes? Okay. This is the same landscape, but rendered in offline renderer, especially made by me. And it shows the also 2 or 3 iterations. Geometry was old, generated. No artist was doing anything. It's all procedural. Just few some, of course. Procedural is well, how to make full screen. This is full screen. Okay. This is Voronoi deformed by a noise. And some cells are moving. This is lava. Okay, do you have any questions so far? Actually, I don't have many more things to show, but any questions about it? The Voronoi or... About recursive things.
How long did it take you to develop these tools?
Oh, that's... for example, this tool in this presentation, oh, I forgot to tell you, of course, it's 64 kilobytes big. Actually, 15.7. And it took me about 2 weeks. Oh, why it's so slow? That's interesting, maybe because of this. Yeah, 2 weeks, but oh, it got slow, very slow.
I mean the tool for configuring these 3D models. 3D
This stuff.
Yeah.
Yes, I did it just 2 weeks before the party, but I had a prototype in suboceanic. I can show you the original suboceanic modeler, and it's tools. Yes, it's called AdSphere. This is really nice. This was oh. Yeah, you might recognize. This was not that easy to use. Yes, but it has bugs in the skinning algorithm. So I mainly reused. Something is broken here. Oh, this is, you may recognize it was at the beginning of this intro, and it really, those are rows. I don't know if rows are not many, much more spheres in rows than in final model. No, that would be bad. Okay, so it's really growing, let's say, and that was the prototype. That tool I did in few days because I just had quick idea and was working late at night, and it's very simple. It's just spheres, and you have the same capabilities of rotating, but I don't. It works for hand. You also have. This was actually more advanced. This is the octopus model. This is for a single octopus, let's say, hand. I don't know what the English word for it. Okay, so but generally it's not the programming part. It doesn't take me so much. What takes me so much is the research and thinking about how to do it, inventing this algorithm. And I really working mostly full time, and I just finished. I was doing as a master thesis also, and I'm doing it from 3 years or 4. So it's really not countable in time. Hard to count, yeah. Any other questions? Yes?
You're adding to it. It reminds me ZBrush too. There are overlapping stuff about your tools and the latest ZBrush simulation. I'm a graphics and not a programmer, so I noticed that there are very similarities between your tools and the commercial one.
Yes, I actually don't use ZBrush. I know I have had problems to figure out how to edit in ZBrush. And I don't know how similar it is. Maybe are there any recursion in ZBrush possible?
Sometimes you can use not very using recursion, but the sphere using is very similar. The fact that you can easily add spheres and then extrude them, it's very similar.
Yeah, so it is possible that it's very similar. Actually the skinning algorithm is different because in ZBrush I know you have spheres converted to quads and then subdivided and smooth out. Maybe this is nicer way, I don't know. I did it with cellular. There are some similarities, yes. So it looks like timer got different values because it's getting slow. You can also make some. There's also hidden feature. Let's say worm with a tree as hand. It's very. Oh, there's another octopus. I didn't solve the texturing problem yet. It might be not that easy. You can do some. Oh, the hidden feature, yes. I did some real-time global illumination faked. Okay. Just to the end, I will show that it's a. Okay. Thanks. Thank you for coming.